We should resume. So, hello, I'm Dr. Komura from Metropolitan University. And so, this is a paper session entitled Moving with Style. And we have 3 papers in this session. And the first paper is titled Motion Adaptation of Cascaded Inequality Tasks. And it's authored by Tomohiko Mukai and Shigeru, Kuriyama, and Masaki, Oshita, and Tomohiko will be presenting.
Thank you for the introduction. So, motion adaptation is a fundamental technique to adapt a handcrafted or captured transformation to different environment or another character with different body sizes. In these examples, the captured reaching movement is adapted to the new environment to avoid the obstacle while reaching for the same location. And the tennis stroke is retargeted to a taller character while hitting the ball at the same position. In this stroke, such a kinetical condition of adaptation is called task. A key observation is that there is strict priority order among multiple tasks. In the reaching example, the first 3 tasks must be satisfied to generate a physically possible motion. The fourth is the objective of the adaptation, but the priority order should be lower than these 3. In other words, the adapted motion may fail to reach the target due to the more severe constraints. Moreover, the first and second tasks should be represented as inequality tasks. Of course, we could generate a right-hand trajectory to avoid the obstacle using a motion planning algorithm. However, we think such collision avoidance should be naturally formulated as simple inequality and optimized together with other constraints. The conventional adaptation methods employ space-time optimization or inverse kinematics for deforming the source motion to satisfy given constraints. Ho and Shang use the space-time optimization technique with 2-layered tasks called soft and hard tasks. As shown in this expression, the soft task is formulated as an objective function that is minimized in the least square sense. And hard task is formulated as an equality constraint. We extend this approach using the hierarchical quadratic programming algorithm to deal with multi-layered equality and inequality tasks. This optimization technique is originally used for a prioritized IK program, and we extend it for space-time optimization program of motion adaptation. Here is a brief summary of our approach. Motion adaptation is represented as a relaxed least square optimization with prioritized constraints that is numerically solved using an iterative optimization. The adaptation tasks are designed with respect to these kinematical values. For example, we can specify the right-hand position at a certain time frame. We can also limit the angular displacement between the right knee at the first frame and the left elbow at the last frame. The set of these tasks is divided into multiple priority layers and solved using a cascaded series of QBs. I will explain the details of our approach. So this diagram illustrates the overall procedure of our adaptation. The optimization starts with the short clip of source motion, and the whole motion is gradually updated at each iteration by executing the cascaded series of QBs. Each layer consists of an arbitrary number of equality and inequality tasks. The clip of adapted motion is obtained after several iterations. Here is the basic formulation of each iteration. The optimization variable is motion variation among all frames. The dimensionality of the program is therefore the product of the number of joints and the number of frames. The objective function quantifies the dissimilarity between the adapted motion and the source. Here all variables mu, delta mu and m bar have the same dimensionality. So I mean the duration of motion and the speed of motion are not modified in our framework. The equality constraints are given as linear equality with respect to motion variation. The left-hand side matrix A is the task Jacobian with respect to the motion vector, and delta B is the variation of task variable. For example, the delta B can be the displacement of the hand towards the target location. And the Jacobian represents the relation between the motion variation and the displacement of the hand. Inequality constraints are also defined in the same manner. Ideally, this problem can be solved using standard QP solver. However, some tasks are often conflicted with each other that causes infeasible solution and unstable computation. To tackle this problem, we use the hierarchical QP method. This method divides the task set into prioritized layers and applies the relaxation method for every layer. The equality tasks are relaxed as a term of the objective function, and inequality tasks are relaxed by using slack variable W. The solution of this relaxed program minimizes the task error in the least square sense. So it's a difficult slide, but I should explain ourselves. Next, the optimization result of the first layer is inherited to the second layer as a hard constraint. The least square solution of the equality task is imposed as equality constraint in the lower layers to strictly keep the error to minimum. Regarding the inequality tasks, the feature tasks are still imposed as a hard inequality constraint in the lower layers. On the other hand, the violated inequality tasks are imposed as equality constraint to avoid further violations. Under these constraints, the second layer's tasks are satisfied as much as possible. This process is repeated to the lower layers. The lowest style preservation layer minimizes the difference between the adapted motion and the source, taking into account the temporal coherence. The optimization constraints are all adaptation tasks that are inherited from the all upper layers. So the number of constraints is sometimes in thousands, but still has a feasible solution. Finally, the adapted motion is updated using the optimized variable delta ML and move on to the next iteration. In our current system, the number of iterations must be manually specified. So next I will explain about the adaptation task. The most basic task is defined in individual frames. For example, a joint angle task makes a joint rotation at a certain frame be a specified value, and an angular limitation task maintains the joint angle within a specified range. So we can define several types of tasks about the spatial and temporal relation between two joint configurations. For instance, the pink arrow represents the displacement task on the same joint between different planes. The blue arrow indicates the distance task between the two different joints at the same plane. The green arrow constrains the displacement from the right hand at the plane T1 and the head at the plane T2. Although this example only shows the spatial relation between two joint positions, we can define the relational tasks between two joint rotations. So we can also define more complex tasks by combining these primitive tasks. For example, we can specify the convex hull shape among similar joint positions by combining the spatial length tasks. We can control the curvature of the joint trajectory by combining the displacement tasks, and the center of the mass position can also be specified by combining the joint position tasks. So let me show you some experimental results. First, the reaching motion was adapted to environmental change. The adaptation was applied to avoid the obstacle while reaching for the same location using these 5 types of tasks. The adapted motion successfully avoided the collision by moving the right hand downward earlier than the source. The overall movement was visually similar to the source motion thanks to the styling preservation layer. The computational time was 65 seconds in total. So next shows the motion produced by using narrower range of motion for the torso joint. The character failed to reach the target but maintains the height of the hand lower than the obstacle because the collision avoidance task is actually given as an upper bound constraint on the height of the wrist. By swapping the priority order of collision avoidance and reaching tasks, the hand reached the goal while colliding with the obstacle. Here you may see the jerky movement of the right hand, and this is because the collision avoidance task kept the right hand lower than the obstacles as much as possible, and the right hand suddenly began to move to satisfy the priority order when the reaching task was activated as the specified frame. This shows the result using non-cascading optimization, where the objective function was the weighted combination of all tasks. The left is the result of uniform weighting that produces unnatural behavior because the range of motion tasks and style preservation tasks did not have a sufficient effect on the result. The right was generated by tweaking the task weight according to the importance. The unstable optimization was caused maybe because of the highly nonlinear objective function. The next experiment is the retargeting of backhand stroke from a short actor to taller character using these 4 types of tasks. The post tasks preserve the spatial relation between two hands to grasp the racket using both hands. The task priority was relatively lower than the others because the slight movement of hands is observed in actual tennis play. As a result, the plausible retargeted result was produced using this 4-layer optimization that required about 30 seconds. In this experiment, a walking motion on a flat surface was adapted to the stairs. The trajectory of each foot was modified using these tasks. Especially, the third task was used to preserve the vertical movement direction of each foot. For example, the negative value was imposed when the foot of the source moved downward. So this result demonstrates the adapted motion will preserve the feature of vertical foot movement. Each foot moved down immediately before ground contact and moves upward during the first half of the swinging phase. These behaviors were easily lost without these inequality constraints. So our framework can be applied to multi-character interactions. The source was a walking motion where the two characters passed each other. The adaptation made the white character stretches his right hand to grasp the red character, and the red character tried to avoid it. In the first three, the higher priority was given to the avoidance. The red character successfully avoided the white character. In the next three, the higher priority was given to the grasping. The red character failed to avoid the touch because of the task priorities. In summary, we have applied the cascaded series of QPs to the motion adaptation program and proposed similar novel spatial-temporal tasks. Our method enables stable computation and the flexible design of adaptation tasks. However, the task design itself is unintuitive in our current system. For example, we must manually formulate each task and determine task priority order appropriately. We should develop an intuitive interface for the task design. And it would be interesting to learn an optimal set of adaptation tasks from the motion capture dataset. A major problem of our approach is the high computational cost that is required for solving high-dimensional QPs multiple times. Moreover, the current method is purely kinematic and cannot incorporate physical features such as external force and inertia. At least we should explore a way to manipulate the speed and duration of motion. So that's my talk. Thank you very much.
Questions from the audience?
Thanks for the interesting talk. So my question is that another approach I think for such problems is to convert the, not using the inequality tasks initially, and then if they are broken, converting them to equality tasks and then doing a resolution. Have you compared your approach to such traditional approach, and what would be the main reason to go for this approach instead of that one? Because it feels like, you're increasing your system matrix size by considering the inequality tasks, since the beginning. Even if, let's say, they are not broken.
So, my motivation is introducing inequality tasks in multiple layers, so such a problem cannot be solved in the traditional approach. So I think this is the first step of the preliminary work to such a direction. So we will simplify this approach and reduce the size of the matrix to increase the computational performance.
Any other questions? Maybe some simple questions. So what if you just prioritize all these constraints by some weight and use soft constraints to solving them all at once? Is that going to be is that what you were showing as a failure case?
You mean how to prioritize a task?
So did you compare your method with putting all the constraints into, soft constraints and changing the weights for each of the soft constraints based on the priority?
So the task, in this experiment, we empirically set the task weights. So So I didn't examine much about the task weight.
Any other questions from the audience? Okay, so then let's thank the speaker.